Understanding how a helicopter works involves delving into a complex interplay of aerodynamics, mechanics, and engineering principles. At its core, a helicopter achieves flight through the interaction of rotor blades, the main rotor system, tail rotor, if applicable, and various control mechanisms. Let's break down these components and their functions. 1. Basic aerodynamics of rotors. Lift generation. Unlike fixed-wing aircraft that rely on forward motion to generate lift over wings, helicopters use rotating blades, rotors, to create lift. This lift is produced by the pressure difference between the upper and lower surfaces of the rotor blades as they spin through the air. Angle of attack. Each rotor blade has an angle of attack, which is the angle between the chord line of the blade and the oncoming airflow. This angle changes continuously as the rotor spins to maintain lift. 2. Main components of a helicopter. A. Main rotor system. Rotor hub, the central component that connects the rotor blades to the helicopter's mast. Rotor blades, typically made from composite materials or metals like aluminum, these blades are aerodynamically shaped and vary in length depending on the helicopter's design. Swash plate assembly allows the pilot to change the pitch, angle of attack, of the rotor blades cyclically and collectively, thereby controlling the helicopter's movement in different directions produced by the main rotor. Without it, the helicopter's body would spin in the opposite direction of the main rotor due to Newton's third law of motion. Control, controlled by the pilot to adjust the helicopter's yaw, side-to-side movement. C. Engine. Power source, provides the energy needed to rotate the main rotor system. Types, can be piston engines, gas turbines, jet engines, or electric motors, depending on the size and purpose of the helicopter. 3. Flight control mechanisms. A. Cyclic control. Function, controls the tilt of the main rotor blades cyclically as they rotate. Effect, tilts the rotor disc in a particular direction, allowing the helicopter to move forward, backward, left, or right. B. Collective control. Function, changes the pitch angle of all rotor blades collectively. Effect, increases or decreases the lift generated by the main rotor, allowing the helicopter to ascend or descend vertically. C. Tail rotor control. Function, controls the pitch of the tail rotor blades. Effect, adjusts the thrust produced by the tail rotor, enabling the helicopter to maintain directional control, yaw. Four. Flight dynamics and maneuverability. A. Hovering. Achievement, by adjusting collective pitch to balance lift with weight, and cyclic control to counteract drift, a helicopter can hover in place. B. Forward flight. Transition, by tilting the rotor disc forward, the helicopter generates thrust in the desired direction. This tilt also involves compensatory adjustments to maintain stability. C. Autorotation. Emergency maneuver, in the event of engine failure, the helicopter can enter autorotation. This uses the upward flow of air through the rotor blades to maintain rotor RPM and control descent speed for a safe landing. 5. Advanced systems and technologies. A. Fly-by-wire systems. Automation, replace traditional mechanical linkages with electronic controls, enhancing flight stability and control responsiveness. B. Composite materials. Advantages, reduce weight and increase strength compared to traditional metal alloys, improving performance and fuel efficiency. 6. Safety and maintenance considerations. A. Pre-flight checks. Importance, ensure all systems are functioning correctly before flight to mitigate risks. B. Routine maintenance. Necessity, regular inspections and maintenance to uphold safety and operational efficiency. 7. Future trends and innovations. A. Electric and hybrid helicopters. Emerging technologies utilize electric propulsion systems to reduce emissions and operational costs. B. Autonomous flight. Development, advances in AI and sensor technology pave the way for autonomous or semi-autonomous helicopter operations.